Hello, hello. We're going to talk about these questions here on the back of our packet, 171, 172, and if I get time, I'm going to stick 173 on there. So let's do it. The question is one of design. It's been a long time since I did a question like that, so I'm really excited to see a question like this. It says 8 people who suffer from hay fever volunteered to test a new medication. So we know that this is going to be an experiment. So a lot of times we have to get volunteers for experiments because we have to give these people a treatment and you have to be willing to take a treatment. So in this experiment, it says we're going to figure out if the medication will relieve their symptoms, and here are the 8 volunteers. 4 of them are going to get the new medication. And 4 are going to get placebo. So that seems pretty good. So people are going to get stuck in either this group or that group. And then because we did that, we'll be able to compare results. And these are the 8 people. So we want to make sure 4 people get into the new med and 4 people get into placebo. But we want to make sure that every person in the test group had an equal chance of being chosen for either group so that there's no lurking variables. So one way to do that is that we can use a list of random numbers. That's a totally okay thing to do. And we can read it left to right. We want to make sure we randomly selected. So we're going to assume they randomly gave us this list. And we're just going to go through the list. And there's a couple little rules for going through a list. So right now, we only want one digit. Right? 1 through 8 only has one digit. And anytime we see 1 through 8, that's going to be in our selection group. So I see the number 0. I'm just going to ignore that. I see 7. So 7's in my selection group. I see 1. So 1 is in my selection group. I see 1 again. So I just ignore that or skip that because I've already selected 1. I see 9. That's not in my numbers. I see 9, not in my numbers. I see 7, not in my numbers. Well, it already picked it. I see the number 3. Okay, so 3 is in my selection group. And 3 again, so I just ignore it because I already picked it. And then the number 6. So these are the people that made it to my selection group. And now because I only wanted to assign 4, I'm going to stop. So the people that are going to get the first selection group will be assigned. And those people, and it doesn't really matter which way I assign. I could flip a coin for that too. But anyway, let's see which name. So I'm looking for Zavala. So I like that name. Then Longquist. I'm already excluding B and E. Then Elifrist and Klein. So definitely my answer here is C. That has the 4 names I selected. C is my answer. Next question. A child is 40 inches tall, which places her in the top 10% of all children of similar age. Okay. So we got this. Height is approximately normal. We have a mean height of children of that age is 38 inches. We don't know the standard deviation. It seems as if we may be talking about a full-on population, so we don't know the standard deviation. We know the mean, mu. And it says a child that's 40 inches. So at this position, 40, we know that that's in the top 10%. So that means she's in the 90th percentile, which also means the area under the curve here is 0.10. We could also think of it from a different way, that the area to the left of the curve is 0.9. That's saying the same thing. So we got to calculate the standard deviation. We can totally do that with our regular old formula and I think that's the way I did it, AP Statistics. I can calculate a z-score working backwards from my table A. So if I look in my table A, under my scores, it appears that a z-score that has an area or a probability of 0.9 happens to be a z-score of 1.28. So a z-score of 0.9 is 1.28, and it does look like it's about 1, so it looks like it's a little more than 1 standard deviation above the mean, the position 40. And so now we can plug in our values. The actual amount of the child is 40. The predicted is the number 38. And notice we know every value except for S. So we can just use algebra. 40 minus 38 over the standard deviation should equal to 1.28. So that would be 2. 40 minus 38 over S is equal to 1.28. And if we cross multiply here, we have S times 1.28 equals 2. So I divide 128 on both sides, and I get standard deviation 1.56. Bam. 1.56. That's my answer. Now, how could I have done that on the fancy calculator? So let's take a look. If I turn that on, and I say to myself, I think this is a distribution problem because it's normally distributed, but I think I can do inverse because I actually know the area under the curve. Well, the challenge here is that the area under the curve, I need to know both of these items. So this would be a good way of checking my answer. If the area under the curve is 0.9 and we were given mu as 38 and we solved the standard deviation as 1.56, we should get the value of 40. And we do. We get the value. That would round to the number 40. So this would be a good way of double checking my answer. Awesome. I'm going to go ahead and do the last question here, 173. It says a study was done to compare the effectiveness of two different teacher groups. One group, or 15 different measurements were used. In all the cases, the mean scores of an SRS of the students, of the teachers from group A, were higher than the mean scores of B. The report of the study stated that in 2 of the 15 samples, the sample size was too small to verify whether or not there was a distant difference in the statistical significance. So let's try to figure out what was happening here? What went wrong? Because it appears as if in all cases, mu A was greater than mu B, which sounds like that should be enough evidence. We're presuming that H sub O, or the null hypothesis, is that they're the same. And we ended up gathering information proving that group A was bigger than group A, bigger than group B, but there still was no statistical difference. And this has to do with the power. If we have some amount of evidence, but not statistically enough evidence, then it's probably what's happening is alpha was too low, or we needed to increase the power in order to detect the truth. And we believe that the truth was that A is bigger than B, and we have a lot of proof that A is bigger than B, but we ended up getting outcomes that were not statistically significant enough. And so this is exactly what happens when we have too low of a power. So if you want to increase power, we want to increase alpha or increase N. And notice it does appear as if N is too low. So if we would have increased N, we would have increased the power. And the reason why we did not detect the truth is because our power was too low. Why was our power too low? Because we didn't increase N enough to be able to have enough power to detect the truth. Thanks for joining us.